Okay, welcome to lecture 20. So today we're going to be covering topological sort and strongly connected components. So topological sort, which is the first part, is a way you're given a directed graph and you try to find a way to order the vertices such that if you can reach j from I, then I comes before j. So this is useful in, for example, if you have dependencies. For example, in your classes, you have prerequisites. You have to take this class before that class. So ideally, there should be a way to order the classes such that you can take all the prerequisites that before you have to take the class. So you don't get something like A is a prerequisite of B, B is a prerequisite of C, C is a prerequisite of A. You don't have this weird catch-22 because then the graph contains a directed cycle. So it's not what's called a directed acyclic graph, a DAG. So we want, given a graph, we want to be able to, given a directed graph, we want to be able to either order the vertices in this way or actually say, okay, there is a directed cycle, so there's no way to order them like this. There's a catch-22 in there. So we are going to use the example from my version of the book from way back in the midst of time when people still wore watches, and I suppose some people still wear ties and jackets. I think I may have worn a tie to that snowball thing last year, and I don't think I've worn a tie since. I don't wear, and I probably wore a jacket. I think I may actually have worn all of these things except a watch. Topological sort, we use depth first search. It's pretty simple. So remember depth first search, you have a stack, so you start at some node and you put it on the stack and you keep track of which of its children you already visited. And so you pop the thing off, you look at the thing on the stack, and if it has a child that hasn't been visited, then you push that on the stack, and otherwise you pop it off the stack, okay? Okay, I should say that for proving things, exercise in the book, it's very important that you have what's called in the book, I think it's called a discovery time and a finish time. Some people call it an opening time and a closing time. So the opening time is when a vertex first goes in the stack, and the closing time and the discovery time, whatever you want. Closing time, the finish time is when it gets popped off. Okay. So this is topological sort via depth first search. We're going to do another algorithm for topological sort at the end, just to show you sort of a neat data structure and a different way of doing this. Okay, well, since I don't have volunteers, I'm going to pick one. I'm going to say, okay, in the book, you pick, yeah, they pick shirt, so let's not pick shirt. Let's pick pants, okay? In the book, they choose shirt. So what you do, you push pants first. And so it gets an opening time of 1, okay? And then I suppose I could write the algorithm, which is just simple. Okay. I'm going to write it the way they have in the book. So they don't actually say pick a vertex B. DFS from B. If well, okay. So the version in the book is not super helpful. So while there is an unvisited vertex, pick an unvisited vertex P, DFS from B. And while okay, this is going to go away. And then order the vertices in reverse order by finish time. So I'm going to explain why this works. But first, let's say we choose pants. So pants goes on the stack. It gets opening time 1, discovery time 1. Okay, so it goes on the stack. You look around, you say, okay, well, what else can we put on the stack? Belt. Belt goes on the stack. So it gets 2. And then, okay, from belt you can get to jacket. So it gets this opening time 3. And then it gets closing time 4. And you pop it off because you can't get anywhere from jacket. And then you go back to belt, and you can't go anywhere from belt, so it gets closing time 3. Oh, sorry, I should be writing this down. 1, 2, so this gets 2, 3, sorry, 4. So this gets, so you can't get anywhere from jacket, you popped it off, you get to belt, it gets, you can't go anywhere from belt, it gets time 5. And then you go back to pants, and you can't go anywhere from pants, so it gets closing time 6. Okay, but you're not done because there are other unvisited vertices. For example, you could visit shirt. Okay, so you choose shirt, and it gets opening time 7. And then you can go to tie, and it gets opening time 8. But you've already been to jacket, so you can't go to jacket again. So you get closing, so you close tie with closing time 9. And then you go back to shirt, and you can't go anywhere from shirt because you've already been to belt. So it gets closing time 10. Okay, so you have to keep going. So you say, okay, how about undershorts? So you say, okay, it gets opening time 11, but you can't go anywhere because you can only get to pants, and pants you've already visited. You're not allowed to visit stuff twice. So it gets opening time 11 and closing time 12. And you pop it off the stack very quickly, and then you say, okay, oh, rats. We could have gone to shoes. I didn't see shoes. Wait, yeah. We could have gone to shoes from, okay, foop. So let's undo all of this. So when we go, we went, oops. 1, 2, 3, 4, close, 5. Okay, pants was still on the list. Pants was still in, sorry, not the list, the stack. So from pants, you can go to shoes. So now shoes goes on, it goes on with opening time 6. But you can't go any from shoes, so it gets closing time 7. And then pants gets, so it comes off, gets closing time 7. Comes off, pants get closing time 8. You can't go anywhere else, good stuff. Now we're going to do shirt. So shirt. Okay, I'm sure you don't need to see this. Shirt goes on with 9, then tie goes on with 10, then you can't get anywhere from tie, that's new, so you get closing time 11. You pop it off the stack. Shirt, you closing time 12 because you can't go anywhere new. Now, undershorts, you get opening time 13, closing time 14. Watch, opening time 15, closing time 16. Socks, opening time 17, closing time 18. Okay, so what is the reverse order of by finish time? So it's going to be socks, which is 18. And then watch, which is 16. And then undershorts, which is 14. And then shirt, which is 12, and tie, which is 11, and then pants, which is 8, and belt, which is 5, and belt, which is 5, and jacket, which is 4. Jacket, which is 4. So, if we draw this, wait, where are shoes? Right, shoes go in here. Pants, shoes were 7, and then belt was 5, and jacket was 4. So let's see. So if we do it in this order, well, there are 2 ways to show this. We're going to do 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so is this a valid order? Could you put the stuff on? Could you put your clothes on in this order? Socks are before shoes. Fine. Watch is before, like, whatever. Actually, you can put your watch on anytime. So, do you put your undershorts on before your pants? Yes, 3 comes before 6. Do you put your pants on before your belt? Yes, 6 comes before 8. Do you put your pants on before your shoes? Yes, 6 is before 7. Do you put your shirt on before your belt? Yes, 4 is before 8. Shirt before tie? Yes, 4 before 5. Tie before jacket? Yes, 5 before 9. Belt before jacket? Yes, 8 before 9. Wow, so we can get dressed in the morning. 3rd year of university, and we learn this stuff. Good. Actually, the first time I taught this, I think I messed it up. So in the next class, I actually showed up in in a tie and a jacket and everything. I'm not sure I actually owned a watch. But I sort of wore this stuff just to show the students that I might have made a mistake in computer science, but I could actually get dressed. So you can also draw in socks, go to shoes. You can also see that this is going to shoes, pants. You can see that this is, if I could actually fit this all in one line, watch doesn't actually point to anything. Undershorts. Okay, undershorts point to pants. So in general, I'm going to go this way, and then I'm going to come back and go this way. Shirt is going to go to belt and tie. Tie is going to go to jacket. Okay, and belt is going to go to jacket. And pants are going to go to belt. And shoes, yeah. Okay, so you can see that you go along here, and you never have to go up or in the same line go backwards. Why does this work? Well, okay, so it's a pretty simple reason. So if when you start at a vertex, anything you can reach from that vertex must either have been visited already, in which case its closing time, its finish time, is before yours. So if you start at V, everything you can reach from V has either been visited or will be visited, has either been visited and already closed. So its closing time is before V's closing time, finish time, whatever it is. Or you're going to visit anything that you can reach from V that hasn't already been visited. You're going to visit during this DFS starting at V, because the thing is reachable from V. So if it hasn't been visited, you'll visit it. That's what DFS means. Which means that you'll visit it, and then you'll visit everything you can reach from that, and then you'll come back and close it, and then you'll come back to V. So everything that can be reached from V has an earlier finishing time. Therefore, this finds a topological sort. Ooh, yay. How fast is this? Well, you can do this with, okay, so you can implement a depth-first traversal in OMN time in, just using, I guess using an adjacency list in this case makes it easier to get OMN time. With an adjacency matrix, I guess it's going to be kind of a pain because you actually, okay, so adjacency list. Woo, isn't this exciting? Okay, so let's spice things up a little bit. I hope this is recording. Oh, yeah, it is. 19 minutes. So, easy algorithm, totally valid to ask on an assignment or a final exam or something like that. Yeah, not one of the ones I usually don't bother to run. Sometimes I can reconstruct it when I need it. It's not very hard. I think I can reconstruct it by now. I must have taught it how many times? Okay, so let's do some exercises. Because everybody loves exercises. Not really. Probably not. But professors say these things to try to convince themselves that Everyone is, oh no, actually it's still topological sort. Yeah, but I'll erase the depth if you want to search. So this is one of the things, actually, you frequently do this as a pre-processing step to make your other algorithms work. So one of the things, I think I picked this up from a professor I was TAing for, and he would tell his students, look, if you don't know what else to do on a question, on an exam question, just write down, and you have to write something. It's not one of these questions. It used to be if you write nothing, you get 1 mark, and if you write something and it's wrong, you get 0. So because they didn't like marking wrong answers. But in the cases where they didn't have that marking scheme, they said, look, you have no idea what to do, right? We sort something. We sort the input. Like, it doesn't matter if you know what you sort it by. Just write we sort the input. Because it's frequently a good thing to do. So topological sort, it's okay. If we don't know what else we're going to do, maybe we're going to sort the graph. So let's see. So there is 23 okay, so the first exercise is show the ordering of vertices produced by topological sort when it is run on the DAG of figure 23.8. I'm not going to do that because that's just the same as what we just did, except for a more complicated graph. I'm standing over here because I have the book here. So, okay, so then this gets fun. Oh no, I'm not going to do this one. I'm going to tell you about this one because I was looking at this, and this is the problem with having a version of the book that is from the 90s. The next exercise is actually wrong. There are many different orderings of vertices of a directed graph G that are topological sorts of G. Well, depends. I mean, if G is a path, there is only one. But okay. Topological sort produces the ordering that is the reverse of the depth first finishing times. Show that not all topological sorts can be produced in this way. There exists a graph G such that one of the topological sorts of G cannot be produced by topological sort no matter what adjacency list structure is given for G. That is wrong. So I was sitting there thinking, like, I can't do this. I don't think there is. I can't come up with an example that I can't come up with a graph in a topological ordering where I can't get that. And so eventually I figured, I don't do this. I was really thinking, I thought, I'm pretty sure this is wrong. So I went looking, and yes, it's in the erratum. Sorry. There is an erratum in the errata that says that, yes, that is incorrect. So I'm going to put it on the assignment 6 for why can you always get, if you get a DAG, why can you generate any topological sort? Then 23.4-3. I'm not sure if these are probably not the same numbers in your version. But, okay, because you are young and still full of hope and not hauling around books for the past 25 years. Well, maybe, I mean, some of you might be. But probably not this one. Although, maybe. Okay, given an algorithm, give an algorithm that determines whether or not a given undirected graph G equals VE contains a cycle. Your algorithm should run in O of V time independent of E. That sounds kind of hard. I should have written this down first. Okay. So this I'm showing you these to show you that, remember at the beginning of the course, I said one of the things that I don't want you to think is that hardness lives somewhere far away and you can avoid it, because you can change a problem just a little bit and it goes from being easy to being hard. That was why we did Eulerian cycles, and then we did Hamiltonian cycles. Eulerian is super easy and Hamiltonian is really hard. But I made you do them, no, I made you do coloring. Coloring is also NP, well actually, determining if there is a 3 coloring is NP hard, and counting them is actually slightly harder. But I made you do it anyway, just to see that you can do interesting stuff with divide and conquer. So I'm going to show you that in the book, you get, I think this is very cute, you get one question which is super easy, which looks hard, but is super easy. Give an algorithm that determines whether or not a given undirected graph, or not a given undirected graph contains a cycle. Oh, so this question is going to be super easy. It doesn't look super easy until you read it carefully, and then you realize it really is super easy. The next question is not. It's actually, well, the answer is super easy, but it's about something. You'll see what I mean when we get there. Your algorithm should run in OV time independent of size of the edge set. So it should run in time linear in the number of vertices, independent of the number of edges. And you think, when you first read that, you think, if you don't read it carefully, you think, that sounds hard. How do you do that? But the key is this pair of characters here, okay? Undirected graph. If it were a directed graph, I think this would actually be impossible. But it's an undirected graph. What do you call an undirected graph? That doesn't contain cycles. Well, if it's connected, it's a tree, and if it's not connected, it's a forest. Okay? So actually, this is just the case that you're going to pick some vertex, so it's undirected, and you're going to do, oh yeah, okay, well, no, I think you can actually do a BFS or a DFS, because normally in a graph, that's going to take time proportional to number of vertices plus number of edges. But this time, yeah, because you can stop as soon as you hit anything that you've seen before. Anyway. So the trick is, I won't do this one on the fly because I want to show you the next question. But yes, so I was thinking about this, thinking that this sounds hard until I realized that it's undirected graph. In which case, you're just checking to see if something is a tree or a forest. So that's It's not hard. I mean, you can do it with... I didn't actually bother to think about how you could do it, and it's very hard to think on my feet talking to the camera. But I could do this. Okay, but the interesting question, you could do this too, I'm sure. But I'm not so sure that I'm going to put it on the exam, probably. Okay, but the next question is interesting. Prove or disprove. If a directed graph G contains cycles, then topological sort G produces a vertex ordering that minimizes the number of bad edges inconsistent with the ordering produced. Okay, so this is an interesting question because it's not actually hard to show that this is not true. One of the ways would be arguing that is it true? Could you get any? We just argued that you can get it for a DAG. You can get any topological ordering. Is that going to hold true if you put some bad edges in and it contains cycles? Maybe not. But probably you can get a variety of vertex orderings. But the so it's not true. And another more interesting way of arguing that it's not true is this problem of finding a minimum, not a minimal, but a minimum. A minimum means it's as small as possible, and minimal just means that you can't take anything, you can't take anything away and leave it. So for example, it's quite easy to find a maximal clique in a graph because you just greedily add to it until you can't, and you can do this in polynomial time. You can't add anything else, and with it still being a clique. A maximum clique means it's actually bigger than any other clique in the graph. That's hard to find. I'm just checking that you can actually find a maximal clique quickly, and I believe that's the case. Yes. I'm a bit unfocused today too. But the question of finding a minimum set of edges that you can remove from the graph and leave it as a DAG is called the feedback arc set problem, and it's NP complete. Well, okay, the decision version, where you're given some threshold. The optimization version is NP hard. So, no, we can't. So this is not true. You can't do that with topological sort, which works in n plus m time, because, or at least we don't believe so. Okay, so you definitely can't do it with topological sort. We don't think you can actually do it in polynomial time, because that would mean that p is equal to np. The reason I was saying this is interesting is because you can imagine, you go out into the working world and your boss says, oh, here is this directed graph, sort the vertices, these are dependencies, you have to have, this is some chemical reaction, you have to have this before you do get this, you have to do this before you do this, whatever, these things lead to this, and your boss says, okay, find an ordering such that we can get from the beginning to the end. And you say, okay. And you run topological sort, and it comes back and it says, okay, there's a cycle. And your boss says, oh, that's very bad. We can't order these things. Okay, I understand the problem. Find the minimum number of edges to remove from the graph. It also works for vertices, feedback vertex set. And find the minimum number of edges to remove from the graph such that it becomes a DAG, and we can order them like that. And in that case, you have to be able to know, to say, sorry, not going to be able to guarantee do that in polynomial time. In the worst case, there are approximations, there are heuristics, but you are now beyond what we know how to do in polynomial time in the worst case. I think. I will check this and send a correction if I'm wrong. Maybe I'll just ask a friend. Feels like Who Wants to Be a Millionaire or something. But no, I'm pretty sure this is feedback arc set. Okay, so that's 37 minutes. Okay, but I just want to do the last question, because it's interesting, and I'm going to use 45 minutes, which is half the lecture, which is fine. Well, okay, it's not following Dowell's rule about breaking things into nice little chunks, but we're nearly at the end of the course, so just grit your teeth and survive, and come on, stay with me, hang on, just like 2 more weeks, 2 more weeks. I mean, I actually like teaching this course, but not like this. Talking to a camera feels so weird. And it's really hard to get motivated. I mean, yeah, okay, when there are students there and I can't check and I can't erase or pause or anything, then it's easy to make easier to make myself actually practice and have the not that I'm super practiced anyway, but it's easier than when I'm going to get up in front of the camera. But it is, look, it's nice high resolution. You can read the board. Okay, so am I gonna write this, or am I just gonna read it? Okay, so this is topological sort, but not using DFS exactly. So another way to perform. Actually, why don't I pause this and write the question on the board, and then we can come back and I'll just read it to you and we save a bit of time. Okay, so Aren't you glad you skipped me drawing all this stuff? So another way to perform topological sort on a directed acyclic graph, I have to stand on this side to be able to read this off the screen. DAG, I mean, if you get anything out of this, just remember what a DAG is, so that if in future, if anyone says DAG, you know, nod, or like bluff, and then go and look it up. A DAG GVE is to repeatedly find a vertex at in degree 0. That means it has nothing coming into it. Output it, and remove it and all of its outgoing edges from the graph. This actually only works on finite graphs. You can have an infinite graph and it doesn't have a vertex within degree 0, but it's still a DAG. And you can actually talk. I mean, think of the integers. And remove it and all of its outgoing edges from the graph. Explain how to, fortunately, I mean, in real life, we don't actually deal with infinite stuff that often. Explain how to implement this idea so that it runs in time O size of V plus size of V. What happens to this algorithm if G contains a cycle? First, let's run this algorithm. So, do I want to leave this here? No, let's get rid of it. Okay, so we say pick one, like, okay, N has nothing coming in, so we output N. N is called a source. Stuff that have some things coming out but nothing going in are called sources, and things that have stuff coming in but nothing going out are called sinks. We will review this when we get to network flows. Okay, N. Okay, what else? P. Okay, what has now O? Didn't have in degree 0 before, but now it does. Okay. Now S. Now M. Okay. Q. R. U. T. If I had students, I would make you volunteer, like, what's going to be the next thing to go, but I have students. If I had students listening, now, I'm not. Okay, what? V. No, wait, we can't do V. It has something coming in from Y. Y. Now V. Now X. Now W. And now Z. And we're done. Okay, that was easy. But how do you implement this in O of size of V plus size of E time? That is N plus M time. So it's not, I mean, you can easily do this in N, M, log N, right? Because you could just do a priority queue. So you have this thing, decrease key. So you make a priority queue. Every vertex is in there with its in degree. And whenever you delete something, you check all of its outgoing edges, and you decrease the priority of all of its all of the things it can reach. And so with a normal priority queue, that would, and so you take things out with delete min. So with a normal priority queue, that would take O v plus e log v. If you do this Fibonacci heap priority queue that we discussed in one of these previous lectures, then it would take v log v plus e because the decrease key is constant time, but the delete min is still logarithmic. But this is still not what we want. We want to stop. Oh, it's 45 minutes. We want to do this in O of n plus m, O of size of v plus size of v. So you can use a cute trick, a data structure. First of all, you can sort the vertices by their in-degrees. So you can calculate. I mean, you can scan the graph. You can look at the in-degrees. That's pretty easy. You can compute the in-degrees. You can sort by in-degrees because remember when we were doing sorting and lower bounds on sorting, I said that if all of the numbers are from a small range, you can sort them using direct addressing. So this is everything is space within linear space, all of the in-degrees. So you can do this easily. And then, so you can make what you're going to do. This is a neat trick. So it shows you why people think this is. I mean, I know we've gone over that data structures are useful for algorithms. You augment data structures. You do this with data structures. You do that with data structures. But here's a trick that shows you that you can actually get rid of this annoying logarithmic factor. So what you do is you put all of the vertices in a doubly linked list. So it's a doubly linked list. Everybody has its in-degree as its priority. And let's suppose that is, so let's just suppose we have like 2, 3, 3, 3, 3, 4, 4, 5. So you have everybody points to, so you know where everybody is. You have a couple of extra little tables, and there's probably other ways to do this, but this is cute. So also everybody is going to point to their predecessor, their successor, and they're also going to point to the leading vertex that has the same priority. Let's suppose this is 4. Okay, just to make it more interesting. Okay, so this one points to itself, this one points to itself, this one points to itself. Well, maybe we have another one pointing, maybe we have another one that's called 4, in degree 4. So, is this recording? Yes, good. Okay, so the thing is, so now, what do you do if you say, okay, so the vertices with degree 0, always at the front. There are other vertices here with degree 0. Well, first thing, what happens if there's a cycle? Well, you take sources off, vertices within degree 0, until eventually, if there's a cycle, you're going to get to the point where there's still stuff left in the graph, but everybody has an incoming edge. So you can't take anything else. There's nothing else within degree 0, but there are still things left. So that means that you've found a cycle. Not everything left has to be in the cycle, but but nobody is a source. Okay, so what happens, so you can take stuff off with in degree 0, and then everything that it points to you go through and you change its value. Now the cool thing is, to say you want to promote this one to a 3, okay? So what are you going to do? Well, okay, it might be that this is 2's, and so there is no 3, but you can cut it out of the list pretty easily. You make this the predecessor of this, you make this the successor of this, so you take it out of the list, you follow its pointer to the beginning of the sublist of the vertices which have the same in degree, and then you put it in here. So let's suppose you cut it out of here. And then you're going to put it in here. So you manage to find here, because it has a pointer to this. You put it in here. It now has priority 3. You look, if this is 3, then it points to wherever this one points to. And if this one had 2 or 1 or something, then it would point to itself. Okay, so that's easy as long as you're not asked to decrease the priority of the first node in the sublist, because everything in the sublist is pointing to this one. So if you cut it out, you have to reset all of these pointers. Okay, so what do? I like this because it shows why you should think in terms of pointers instead of just starting immediately with object-oriented programming, because I think it's much more natural to do this if you've learned C than if you've learned Java. Because, well, see if you agree with me. What you're going to do, you have these. So everybody is pointing to this one. And you want to decrement this to be a 3, and everything is a 4. But if you just try to cut this out of the list, you ruin all of these pointers. So what you do is you actually take the stuff that's in this memory location, and you put it here, and you swap these two. So this is a 4, and it has maybe it's pointing to some other stuff. It says hello or something. And this is pointing to world as satellite data. So what you do is you actually take everything that's in this struct, in this node, and you switch the contents, but you leave the memory locations as they are. Sneaky, eh? So what you would do is erase this, and all of this stuff, all of the associated fields would come over. And this 4 is now here, this 4 is now here, this is now hello, this is now world. And now you can, so this is actually, if this was 4, if this was, let's say, this was U and this was V, then you swap them, which maintains the order. So it still works with hello world, but in this particular instance it works. If this is U and this is V, you swap them. And then now you're in the case where this one you can just cut it out of the linked list again. And because it's no longer now, nobody else is pointing to it except its predecessor and its successor. So cute, fun with pointers. That's not actually algorithms, that's data structures, but it's in the Introduction to Algorithms book. Maybe it's not the only way to solve that problem. I'm probably way over time. Yes, I'm at 55 minutes. So in order to get through strongly connected components, I'm going to stop babbling about this stuff. It's just one of those things where it's good to know about data structures because we teach this course as sometimes people think algorithms and data structures, but it's actually, data structures are to do algorithms, and algorithms, you use algorithms to build data structures, and you use data structures in algorithms. So it's really, I mean, people focus on different areas. I'm more a data structures person. But there's a lot of interplay. Okay, that's good. Okay, don't worry. I will stand. Was I blocking out for all the time? Yeah, maybe I was standing right in the way, was it? No, you can still see it, sort of, I hope. Anyway, 56 minutes. I have to get on with strongly connected components. Okay, so see you in a few minutes.